So this is our first YouTube video for Physics 10. Right now we have covered up to, I think, chapter 8 in the book. This will be the last chapter before the test. I don't know if you've been getting the information on Canvas, but there's going to be an online test. The test will come online Monday. It will stay on for an entire week, and I think it's 50 multiple choice questions. If you're going to take it, right here, once you start, you have 2 hours to finish it. So don't take the test on Monday. You have a whole week to do it, but once you start, you got 2 hours to take the test right there. I think on Canvas, I told you a website that will allow you to review. There's the test bank. Just go onto Canvas and look at the announcements right there. I'm going to give one lecture here on gravitation, which was chapter 9, and then I'll give another one that kind of reviews the earlier chapters right there. Okay, so let me go ahead and get started. This chapter is on gravitation right here. Now, we've brought up gravity before. Remember, we said when something falls right here, we said the force on it is just mg and the acceleration is just g, and we said g was 10 meters per second squared right here. Well, this is not exactly true. Newton never said this right here. It's just that you couldn't handle the truth before. Now I think you're a little bit better at handling the truth. What Newton did say is, he said, if we have a point mass, I called it M1, and we have another point mass, M2, these two masses are attracted to each other. And here I put their separation as D right here. The two forces are attracted with equal and opposite forces, Newton's third law right here. What Newton did say is, he said the force of gravity is proportional to the product of the two masses divided by the separation of the two masses squared. Right? Well, if you're proportional, that means that if I put in a proportionality constant, call it big G, then the force of gravity equals big G, mass of one, mass of the other, over the distance squared. This is called Newton's law of universal gravitation right here. Now that big G, that constant, is constant throughout the entire universe. Newton could not measure it. It wasn't measured until 200 years after Newton's time. And it came out to be 6.6 times 10 to the minus 11. This is a very small number. Which means that this force of gravity is a very weak force. Right? Now, Newton did not know this, but Newton was a good guesser. He guessed 6.5 times 10 to the minus 11, which allowed him to make a lot of calculations right here. So now we can see that mass has a dual role. We said mass before was what? Resistance to shaking. Now we have another role for mass, and that is it attracts other masses right here. So there's a dual role for mass right here. But remember, this is a very weak force. Just to compare, here if I have a 1 kilogram mass and another kilogram mass and separate it by 1 meter, then if I plug in 1, 1, and 1, that's all 1, and it's just the force just comes out to be that little teeny number. That's a billionth of a Newton. You wouldn't even notice that right there. Matter of fact, the only time we ever even notice this force is if one of these masses can be big enough to counteract that little teeny small value of G right here. And where are we going to find a mass that big? Well, the Earth is big right here. And so if we wanted to find the force between us and the Earth right here, well, we would say our weight, which is the force between us and the Earth, you would put the G. Now, one of the masses is the mass of the Earth. The other mass is your mass. And the distance between you and the center of the Earth is the radius of the Earth. And remember, it's a square right there. Now, everything in this green area right here doesn't change much when you walk around the Earth. The radius goes up a little bit when you climb up into the mountains, but it's such a small change that this is pretty much fixed. And if you calculate this, this all comes down to just 10 meters per second squared, and that's why we called it little g before. So this, what we were doing before, was just an approximation right here. This is the true value right here, and this is what you would use if you were going to go way above the Earth or way down into the Earth right here. And so this is much more accurate right here. So this weight right here, weight equals mg, is only good at the surface of the Earth. So when you go up into the mountains, r gets a little bit bigger, the weight gets a little bit smaller right there. So every time you get on the scale, you're measuring that big G, the mass of the Earth, your mass, and the radius of the Earth, all in that one measurement you see on the scale. And if you don't like what you see, you don't have to blame it on that. You can always say, what, the Earth is quite massive today, right here. Okay, now you notice it goes, this thing goes as a 1 over the distance squared right here. Well, the reason, anytime you go as 1 over the distance squared, we call this an inverse square law. The inverse meaning it's in the denominator, square, it's squared right there. Well, the reason why this law is an inverse square law is because we live in 3 dimensions of space. If we look at a light bulb right here, a light bulb emanates light out right here. As light comes out, as you go out further and further, the intensity of the light drops off. You notice if you go out a certain distance and you calculate the area of this sphere right here, now you go out twice the distance and you calculate that area is going to be 4 times bigger. Well, that would mean that this light spread out, every time you double the distance, it spreads out by a factor of 4. Well, if it spreads out a factor of 4, the intensity of that light should drop by a factor of 4. It's spreading out right here. This is exactly what gravity does. Since gravity emanates out from the planet right here, as you double the distance, it gets 4 times weaker. Everything that emanates in 3 dimensions would do this. If we had a radioactive source here and a Geiger counter here listening to clicks, and we heard 100 clicks per minute, if we moved out to there, we would only hear 1/4 as much, which would be 25 clicks per minute. So this is for anything that emanates in 3 dimensions. If we lived in 2 dimensions, what would be like that? Well, suppose you drop a rock on a pond and the wave goes out. Well, that wave is only going out in 2 dimensions. Well, the intensity of the wave wouldn't be an inverse square law, it would just be an inverse law. It'd be 1 over the distance. So if the universe were 2-dimensional and we walked around like this, right here, and we couldn't go around people, then gravity would just be 1 over the distance. If we lived in a 1-dimensional universe, we lived on a line, so we couldn't go around people or climb over them, then there wouldn't be any distance in here, right here. But we live in 3 dimensions. If we lived in 4 dimensions of space, then this would be 1 over d cubed, and there'd be more ways of getting around people than this and this. Don't ask me what they are, but there'd be more ways right there. Okay, so here we are on the Earth right there. Here we are standing right there where our distance is right there, and I'm going to plot out your weight versus distance. Well, we know what our weight is here. It's whatever you weigh in your scale at home right here. Now, as you start climbing on a ladder and going up higher and higher, your weight gets less and less. You notice right here, it's much smaller right here. This thing follows a 1 over the distance squared. So if you got on a ladder exactly the same height as the radius of the Earth, you would weigh 1/4 as much. Up here, triple the distance, you would weigh 1/9 as much. Quadruple the distance, you'd weigh 1/16 as much. So and this never goes away to 0. So gravity emanates out forever. It never goes to 0, but it gets awfully weak right here. Now, suppose instead of climbing up on a ladder, we dug a hole and we went into the Earth right here. and we weighed ourselves down in a hole, in a mine or something. So here I have it over here. Here we are in a mine right there, and we weigh ourselves there. Well, now you might think gravity would get bigger because the denominator got smaller. So if r gets smaller, this would get bigger right here. But it won't. That's not what's going to happen. What happens is, on this formula, when I put in the mass of the Earth, this mass is you only use the mass that's within your radius. Well, when you're out here, all of the mass is within your radius. It's this whole thing. When you're right there, the only mass within your radius is just that blue region right there. So you can see as you go in closer and closer to the center of the Earth, r might be getting smaller, and m is getting smaller much faster. This term right here your weight actually drops, and it will drop just like this. And when you get right to the center of the Earth, you would weigh nothing. Well, you couldn't weigh anything because usually when you stand on a scale at the center of the Earth, the scale has to be below you. Well, there is no below you when you're at the center of the Earth. Everything is above you. You would just float there, so you can't weigh anything there. So here we can see that if you went to the center of the Earth, you'd weigh nothing. And so you can see from this plot where you weigh the most, your maximum weight is right there at the surface of the Earth, right here. You want to lose weight? Climb a mountain, dig a hole, one or the other, right there. Okay. So once Newton came up with this, he could solve a lot of things, get the masses of all the planets and stuff. But one thing he could do is he could explain the tides right here. So let's look at the tides right here. Here I have an object, the Earth right here, and I have another one. It doesn't have to be the sun. It's just some object that's producing the tides on us. Well, because Newton's law, the force depends on the distance, you notice this part of the Earth is closest to the sun, so the force is big right there. This part is the furthest away from the sun, so it's a small force right there, and right in the middle would be halfway in between right here. Well, what does that do? Well, it means the water gets pulled up here because it's pulled harder, and you also get a bulge here because it pulls this part harder than this, so this part's left behind right here. So you get a bulge on either side. And so as the Earth rotates once a day, you're going to go where you get the bulge, no bulge, bulge, no bulge right here. And when you get right here, if that were the sun, then you'd be right at high tide at noontime, because when the sun is right overhead, it's noontime. You would get low tide at, what would that be, 6 p.m. This would be midnight. You'd be back to high tide. 6 a.m. it'd be low tide again. And if the sun dominated the tides, that's the way the tides would go. But the tides don't go like that right there. If you go down to the beach tonight, and let's say it's high tide at 9 p.m. tonight, well, that means if you went tomorrow night, it would be high tide at 9:50. The next night, 10:40. The next night, 11:30. High tides are 50 minutes later each day. So every day you go down there, it's going to be 50 minutes later every day right there. So what does that do to? Well, if we come back to here, let's put the moon in here, right overhead at noontime also. Well, the moon, if the moon is right here, again, we have a high tide. But in one day, the moon is not there. The moon goes around us. It takes 30 days for the moon to go around the Earth. So in every day, it goes a 30th of a turn. So we can make it all the way around here in 30 days. So if it's right here today, tomorrow it'll be right there, a 30th of a turn. So at noontime, it won't be overhead. We have to turn a little bit more. The Earth has to turn before the moon is overhead. Well, the Earth has to turn a 30th of a turn. Well, if it takes us 24 hours to turn, how much does it make to take a 30th of a turn? A 30th of 24 hours is 50 minutes. So the moon is overhead 50 minutes later every night, exactly following the high tides right here. So it's the moon that dominates the tides right here. Now, the reason why the moon dominates, the force due to the sun is much bigger than the force due to the moon. But it's not the force that gives us the tides. It's the difference between this. It's this arrow minus that arrow. For the sun, this is a big arrow, and this is a big arrow. When you subtract the two big arrows, you get almost nothing. For the moon, the difference between these two is not negligible. You get a net effect, and that difference is much bigger than what you would get for the sun. So the moon is its gravitational pull on us with the tides is about 3 times bigger than what it would be for the sun right here. Now, the moon also has tides. You might say it doesn't have water, but it has dirt, and dirt is pulled up too, and so on. So it deforms the moon a little bit. So it's exactly like the Earth is deformed right here. Now, if you've ever looked at the moon, you notice that the same face of the moon always points toward the Earth. We never see the backside of the moon. We didn't see it until Apollo 8 flew behind the backside of the moon and looked. It was always good to look because anyone that's ready to attack the Earth, that's the perfect place to be just before you attack the Earth because they can hide out right there. Okay, so we always see the same face right here. Well, that must mean that the tides don't change. It's high tide here. It's always high tide right there. The moon was probably spinning much faster in its past, but what the tides do is they try to, as the moon rotates, it tries to pull the tide back, and it slows the rotation down right here, just like what's happening to us right here. We're spinning and trying to keep the bulge here. We're slowing down too right here. Now, we don't want to stop. We want to slow down until our tides don't change anymore. That is, until the moon is right overhead all the time. So, well, so the same fate, it's just that the moon is much smaller than us, and he has already slowed down to where his tides don't change. We're slowing down until our tides don't change right here. Now, so the Earth is slowing down. The Earth is slowing, and the moon, the only thing is, if we're losing angular momentum, someone else has to pick it up because you can't destroy angular momentum. As it's trying to put the brakes on us, it's trying to pull us back, we're pushing the moon faster. So the moon is going around, it's picking up speed as we're slowing down right here. As the moon picks up speed, it gets a little bit further away from us, which means it's going to get a little bit smaller in the sky. And so pretty soon it'll be too small to ever cover the sun right here. So you won't get total solar eclipse way off in the future. Well, so this is going to keep slowing down. This is going to keep speeding up but it's going to get out further, and pretty soon, way off in the future, the time it takes for this thing to make a turn will be the same amount of time it takes this to make a rotation, which is the same amount of time that this thing takes to revolve, and that'll all end up at about 53 days. That's going to be way off in the future, past 1 billion years from now, right here. But all of these will be equal right here. If you go to any solar system, if it's really old, a lot of things are all going to be synchronized right here. If nothing is synchronized, it's probably a young solar system right here. So that would mean the year will still be the same, but each day would last 53 days right here. That would mean that you'd get like 7 days a year, 7 days a year. So you'd say birthday every 7 days, and it would last for 53 days. You might want to invest in birthday cakes right here. Okay, so, or candles. Okay, now we can go back into the past right here also. In the past, the Earth rotated faster. The moon was a lot closer right here. When the dinosaurs were around, I think the day was like 18 hours, and the moon was a lot closer. It wasn't a little thing in the sky, it was a huge thing in the sky. You're not running from the dinosaurs. What are you running from? Not the moon, you're running from the tide, right here. Okay, so the tides right here, they've been huge. The moon would have been big in the sky right there. Okay. So Newton was able to explain all of this right here. Last thing I want to bring up is something called a black hole right here. Black hole is a region where gravity is so strong that light can't even get out right there. Well, how do I make gravity really strong? Well, if you were to squeeze the Earth down, as Earth gets smaller and smaller, we can see as the Earth gets smaller and smaller, the R gets smaller. All the mass is still within your radius because you're just shrinking the Earth. So this just gets larger and larger right there. And if you could shrink this down, let's say the Earth down to the size of a marble, then the Earth would all of a sudden become a black hole right here. The reason why they call it black hole is even if you had a flashlight and shined it straight up, the light would bend around and come back. So if you viewed it, you would not see any light coming off of it right here. So that's why they call it a black hole right here. Now, what would happen if you fell into this black hole right here? Well, let's say you go in feet first right here. Well, if you go in feet first, there's going to be a tidal force on you. That is, your feet will be closer than your head. And if you pull someone harder with their feet than on their head, they're going to stretch out right there. And I call that the noodle effect. They'd end up being a noodle right there. And if someone watched you go in, they would see you getting what? Skinnier and skinnier. And time is affected by gravity. They would see time going slower and slower when they look at you, right? If they saw your watch, they'd see it run slower and slower. And they would say, you'd get to a point where you would freeze in time right here. You'd freeze in time because time would almost stop at a certain spot. So you never see anything going into a black hole because they get to a point right here called the event horizon where time freezes right there. So it's a good place for a graveyard because not only do you get to see your loved ones forever, but they're skinny. Okay. Well, hopefully that'll cover this thing for gravity. Okay.